Okay, so what we have learned is the following. So here's a magnetic field into the plane of the paper. What we do is we take a rod and move it with the velocity v. And what you find is this rod develops a voltage. And the EMF is VLV. V is the velocity, and L is the length of the rod. All right, so, so people wanted to check this. And well, I mean, we've done many checks to it and experimental verification to it, but it was important enough for, yeah, I guess important enough. And they checked it using the space shuttle. Okay, so what they did was, so again, the velocity of this rod or this metal conductor has to be perpendicular to the magnetic field. Well, the component that matters in this equation is the component perpendicular to the magnetic field. So let's write that, make sure. The component perpendicular to the magnetic field. Yeah. So they did this using the space shuttle. Here's the shuttle, and they here's a satellite that they released from the shuttle, which was tethered to the space shuttle. And this is 20 kilometers long. The cable is 20 kilometers long, which is 12 miles. Okay, so from Daytona Beach to Ormond Beach. Okay, well, a little more than that. So that long a cable, and the voltage induced between these two should have been VLB 7,800 volts. Okay, 8,000 volts, and they did measure a voltage of roughly a little half of that because of leakage of charges and stuff like that. But so they did verify this using the space shuttle. Okay. Okay, so now we're going to comment on the field, this electric field being a non-conservative field. Okay, so what we're doing is the following. Okay. So we saw that charges produce electric fields, and in this chapter, what we're learning is time-varying magnetic fields producing electric fields. Okay, so so the electric fields have different natures. So let's say this is a charge that's producing an electric field like this. Okay. Now, if you take an arbitrary loop and calculate the electric field around that loop, this line integral will be 0 for this electric field. Okay. Now, the type of field that we are producing be increasing. You saw that the electric field is in this direction. Okay. And in this case, if you take the line integral, it's not 0. Okay. So essentially what we're saying is the electric field produced by these charges, the line integral around the loop, any loop, you can take any loop, the line integral is always 0. So this is called a conservative electric field. In this case, the line integral is non-zero, and this is called a non-conservative electric field. So the electric fields have different natures. Okay. That's what we're saying here. So the electric fields produced by time-varying magnetic fields are non-conservative electric fields. Electric fields produced by stationary charges and moving charges are conservative electric fields. Okay. So these are Republican electric fields, and these are Democratic electric fields, to use a poor political joke. All right, so the magnetic field is into the plane of the paper, and if you decrease the strength of the magnetic field, or you would let me figure out. You're increasing the strength of the magnetic field, and the induced EMF will be like so. Okay. I'm just making sure again. Yep. You're increasing the strength of the magnetic field, and the induced EMF will be like so. And you see the line integral is equal to the voltage around this loop, and that is non-zero. So this is a non-conservative electric field. Okay. All right, so here's an AC generator. Again, like I said, it should really be called a transformer, an energy transformer. You saw that this is how all electricity is produced currently. Okay. Again, all right. So in this AC generator, what you have is a permanent magnet, and you're turning this loop in between this magnet, and you're producing electrical energy. And you have to do work to turn that loop. And there are various technologies. At a dam, the moving water is turning the loop. In a windmill, the turning wind blades are turning that loop. In a nuclear power plant, from the heat generated, you produce steam, and the steam turns this thing. In a thermal power plant, again, the steam turns this thing. Yeah. So you figure out how you turn that loop, and you produce, by turning that loop, whatever input energy you put in is converted to electrical energy. Yes. All right, so that's a transformer, and so for the AC generator, here's the EMF. Okay, as this thing turns, omega is the angular velocity, the velocity at which you turn. N is the number of loops you would have there. A is the area of each loop. B is the strength of the magnetic field, and omega is the angular speed at which it's rotating. Okay. So you saw that the voltage was a sinusoidal voltage, and the amplitude of the voltage is that. Okay. Now it turns out that the rate at which you turn the loops be steady. So the frequency of commercial generators in the US is 60 hertz. Okay, so so what we're saying is, in all those technologies, in the dam, in nuclear power plants, in windmills and all that, you have to absolutely make sure is, in the US, you have to make sure that that thing is turning 60 times a second. This loop is turning 60 times a second. In Europe, it turns 50 times a second. Okay. Now, there are reasons for all of those to be exactly, precisely that. Okay, and it's related to, can I get some water as well, please? Thank you. All right, so that's what that is. So your gears have to be such that no matter what speed the wind is blowing, that has to be turning at 60 hertz. Okay. All right. Okay, so here's a DC generator. Okay, it depends on how you hook up the coil to the external wall. If you hook it up like so, you get a DC voltage. But thank you. Okay, so we won't worry about that. This is, I don't know, you might have seen a toy like this. It illustrates Lenz's law. Okay, so here's a coil, here's a battery. when you close the switch, the current in this coil went from 0 to whatever maximum value fairly quickly. And as soon as current passes, then this produces a magnetic field. And here is a metal ring. So the flux through this metal ring change, and then an EMF is induced in this ring, which is producing an opposite magnet, and the two magnets repel each other. So the induced and this ring will fly up. Okay, and this is a pretty cool demonstration. If you remember the classroom, and this thing can fly up to the ceiling of the classroom. So anyway, so that momentary change in flux causes this to be repelled. Okay, so here's an important device that you all have in your houses. So this is a ground fault interrupter. This looks something like this. If you've seen a plug like this, you can have it in your garage or in your bathrooms and stuff like that. And what this does is the following. Okay. So the insides of that are the following, like so. So this is the incoming line, and there's the outgoing line. So as long as the current through, and this current is producing a magnetic field in that direction. Okay. So what we're saying is the following. You guys remember that a current flowing like that will produce a magnetic field in this sense. Okay. So it's producing a magnetic field like that. All right, so what this means is this current is producing a magnetic field through the loop in that sense. This current is producing a magnetic field in this sense. Okay. Now, if the wires are close by, the net magnetic field through this thing, this coil is 0. Okay, so if this is an AC voltage, AC current, when the current switches, the magnetic fields, when the current is like this guy will produce a magnetic field like that, and the current is like that, this guy will produce a magnetic field like this. Anyway, even whether it's an AC or DC current, in your homes you have AC current. So whether it's AC or DC current, the net flux through this loop is 0. Okay. And so this is the sensing coil. The net flux through this thing is 0, and there's no current through this thing. Okay. Now let's say something like this happens. So you're using a hair dryer or something, and one of the wires gets frayed, and instead of the two currents being equal, some of the current leaks out through the body of the hair dryer through you to the ground. Now the two currents are not equal. So coming back, now the two currents are not equal, and suddenly there's a non-zero magnetic field through this sensing loop. As soon as you have a time-varying non-zero magnetic field, it'll induce a current in this loop. And this sensing coil, as soon as there's a current in the sensing coil, it'll trip the circuit breaker. Okay. So this is an extremely important safety device. It prevents you from getting shocks and stuff like that. Okay. So the flux through the sensing coil is not 0, and the induced voltage triggers a circuit breaker within milliseconds. So this device can prevent giving you a shock within a millisecond. Okay. And of course, when it rains and stuff like that, sometimes there's leakage of current, and this thing will trip, and you have to reset it. Now, a lot of electric guitars and stuff like that, stringed instruments are based on the Faraday's principle. So the string is magnetized, and when the string vibrates, this magnet moves back and forth. And here's the sensing coil. Okay, when the magnet moves back and forth, the flux through the sensing coil changes, and that induces an EMF. Okay, so that motion is translated into an electrical pattern in this sensing coil, and you process that electrical current, that electric current in the sensing coil, and that is proxy to this motion. Okay, and then you can feed that to an amplifier and to a speaker. So currents in the coil are amplified and fed to the speaker. Okay. Now here's an interesting little device. Let's look at the simulation. All right, so here's a magnetic field into the sheet of the paper. Here's just a metal plate, and that's free to swing about this point. Yeah, so let's start this metal plate. We'll swing through this, and as soon as this metal plate goes through this region of magnetic field, you're inducing a current, and the induced current is such that it is sort of, well, it's opposing this flux. So if you think of it as magnets, it's assuming an opposite polarity, and the North Pole and South Pole attract each other, and it slows this current, this device down. Okay. So you induced opposite magnetic polarities, and it stops it. Okay, so this is what is called an eddy current. Okay. All right, let me show you a very important application. Okay, so this is called electromagnetic braking. Okay. And you can use this to stop trains. So for instance, on a train, there's the rail, and I guess this can be the current loop. There's the current loop. So when you want to stop the train, what you do is, instead of frictional braking using brake pads, what you do is, here's the loop. All you do is flip a switch, pass a current through this coil, and just like in the eddy current, this will stop the train. What it does is it induces currents in the rails, and the induced polarity is such that if this was the South Pole, you'll have a South Pole there if the train is moving this direction, and a North Pole here. This South Pole is repelling that South Pole, and this North Pole is attracting that South Pole. So the induced currents are like so, and it will stop the train very fast and very smoothly. Okay, this is electromagnetic braking, and the advantage would be, of course, your brake pads, there's no brake pads, you don't have to warn, nothing wears out, and all you do is flip that switch, and the train stops. Okay, so, and there will be no jerks and nothing. Okay, so all right, so there's the eddy current stopping it. Now if you put prongs in there, now the eddy currents cannot be as, so essentially now you reduce the area of the change for magnetic fields. So the induced currents are smaller, and it takes longer to stop this thing. Okay. So anyway, look into electromagnetic braking. That's a very important. I mean, that's a very safe way to stop trains. They don't actually use it for other reasons. They should use it from a science perspective. Anyway, okay, so here are metal detectors, and the way, so an AC current is applied to the transmitting coil. So now imagine this without the metal detector, without any metal in. So this is the transmitting coil. So here's an AC current applied to the transmitting coil, which is producing a magnetic field, and the receiving coil that induces a current in the receiving coil. So let me. Right, so here's a transmitting coil, and when the current is like this, this induces a magnetic moment like that. There's the north pole, there's the south pole. And so if you apply an AC current, the polarity flips, and the magnetic field is changing here, and you're inducing a current in here, induced current, okay? So the magnetic field switches back and forth. So, okay. Now if you induce a metal, there's an induced current in the metal where the polarity is in the opposite direction. And as soon as you induce a metal, now the flux through this thing decreases. Okay, so if a metal object intervenes, the induced flux decreases in the receiving coil, resulting in a drop in the induced current. So when there's no metal, there's a certain level of current in this receiving coil because of the AC current here. As soon as you introduce some metal, the current in this receiving coil decreases, and that's how you detect metals. Okay. All right, guys, so that finishes this chapter. Let me summarize the slides quickly, and then I'll open the floor for questions. Okay. Okay, so what we were studying was this equation. Okay. There are two ways to produce electric fields. Electric fields can be produced by charges and moving charges. This electric field is a conservative electric field. You can also produce electric field by time-varying magnetic fields. Okay, and this is a non-conservative electric fields. Yeah, so we studied electric fields produced by time-varying magnetic fields. The thing is summarized by Faraday's law. The induced EMF is equal to negative of time rate of change of magnetic flux through a loop. So the induced EMF in this loop, for instance, is equal to time rate of change of magnetic flux through that loop. Now there are several ways of changing the flux through a loop. You can either change the magnetic field, you can change the area, or you can change this angle, or you can change all three at the same time. You saw that in practice, the easiest thing to do is to change the angle theta, okay? And that's what you saw in this application in the generators, okay? So the easiest thing to do is change the angle between the area vector and the magnetic field vector, okay? So, but Faraday's law tells you that induced EMF in a loop is equal to negative of the time rate of change of the magnetic flux through that loop. All right. Lenz's law tells you is related to that negative sign, and it tells you the direction of the induced EMF or induced current. And if you move so what Lenz's law tells you is if you move the magnet towards this coil, the induced current is in this direction. If you move it away, the induced current is in that direction. If you take a metal rod, this is motional EMF. If you move it perpendicular to a magnetic field, there's a voltage induced between the ends of the rod. Okay, so if you move it perpendicular, there's an EMF induced between the ends of the rod, and the EMF induced between the ends of the rods is equal to BLV. Yeah. So this slide shows you that the electric field induced by time rate of change of magnetic flux is a non-conservative electric field. If a line integral of the electric field around any closed loop is non-zero, then that's a non-conservative electric field. Yeah. All right, that covers the topics that we covered in this chapter. Okay. And I will stop recording and